I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Ron DiGiuseppe from Synopsys, who's going to talk today about changes in automotive architectures. Ron, we've seen a lot of things going back and forth in automotive in terms of they've gone centralized, decentralized to centralized, and they've also now electrified the car. So now you basically have to deal with much more data-centric types of approaches than we did in the past. How is this affecting what's going on in the architectures?
There's a significant impact, as you said, that these changes are having both on the applications and the architectures that implement those applications. Right now in the industry, that change is taking many different aspects. One is the type of sensors that are used in the cars and the evolutions of those sensors, the use of much higher resolution image sensors, the new type of LiDAR sensors, new types of radar sensors with 3D radar, 4D radar coming. So the amount of data that is being presented to the processing elements of the car is increased so much that the processing architectures are also changing to accommodate these new amounts of data. So those changes impact both the automotive network, the in-car network for the data, and also where those processing elements, either ECUs or domain modules, or even the new zonal architecture, and how they're architected and implemented.
We've been thinking about autonomous driving, though. I've been hearing about it for at least the past 7 or 8 years in very real terms. So how come now we have to change the architecture? Did they not understand what was going on initially in terms of the amount of data that would be produced here?
A lot of the changes are certainly driven by new applications like autonomous vehicles, automated driving. And that just highlights the amount of processing and the introduction of the AI algorithms. AI is not just solely used in autonomous vehicles, but also throughout the existing architecture of the car, especially like in the ADAS modules that implement the safety critical functions like automatic emergency braking. That function is an AI-based function using a deep learning network, maybe a DNN or a convolutional neural network, to identify those objects and make decisions based on those objects. So those are in ADAS and will be even more implemented in those automated driving autonomous vehicles. But that just highlights that AI for ADAS and for the future autonomous vehicles is an important new development, but it's not just relegated to ADAS and autonomous vehicles. AI is being used in infotainment, and I was surprised more recently that AI is being used in powertrain for EV powertrain management, sensor efficiency, predictive analytics. So AI is even used in powertrain. So that just shows you when you start implementing AI across the different applications, the processing performance of a car is increasing dramatically. And the system architectures have to accommodate that.
Let's drill down into where we are now and where we're going.
Sure.
Ron, what are we looking at here?
Well, Ed, what I was discussing previously was some of those new applications that use AI are generally segmented into various domains, maybe 5 different domains. ADAS being one of the principal domains for taking control of the car, either a level 2, level 2 plus, level 3. But AI is also used in other applications, as I mentioned, such as the infotainment systems, where these new large screens, 42-inch screens that have multiple windows, such as the cluster or the infotainment windows, and also with driver monitoring systems. That would also use AI in the infotainment domain, as well as I mentioned how AI could be used in the powertrain domain. This is pretty much the current system architecture that the automakers are implementing now. Modularized new applications going through a central gateway. And those new applications also need to accommodate the new requirement to support over-the-air software updates, OTA, the electronic architecture to support that, plus with all the connectivity, implementing 5G connectivity, all the other possible connection points in the connectivity domain, with the increase in security, just will increase the amount of compute processing required for the car.
All of this produces a lot of data. What has to happen with that data? Because we can't just process all this data centrally, right?
Sure. And when we talk about data, and I'd like to maybe just highlight first how the different integrated circuits, the SoCs in those various domains, are architected to actually process that new data. As we just discussed, the amount of sensors and the types of data is increasing and evolving. And so the SoCs, the integrated circuit processors that process that data, also change. And this slide just summarizes the different types of SoC architectures that implement the data. A couple points is they'll generally have a multi-core 64-bit processor, but due to the amount of data, will also be a need for some sort of accelerators, either DSP accelerators, AI accelerators, vision accelerators for the imaging, different accelerators for the LiDAR point clouds, the different types of radar, sensor data, sensor fusion. So developing an automotive processing module is way beyond just multi-core heterogeneous processing. It's multi-core with AI acceleration. And that goes across the board in the different types of modules, infotainment, powertrain, ADAS.
Well, we've now had the better part of a decade to focus on this. What have we learned along the way?
Well, we've certainly learned that with the new types of data, there's a transition to higher performance automotive network. So I wanted to showcase that change. This is one of the learnings, which is when we look at the left-hand side, that domain architecture that we already talked about and the new applications, we see a movement in the automakers to implement a new electronic architecture, which is summarized in this right-hand side, a zonal architecture. Based on one of the learnings is by having a more centralized processing module with actual zonal gateway switches and the ability to process some of the sensor data locally in the sensors, that will allow us to accommodate the amount of data and the amount of processing required. So it's one of the learnings is that the architecture needs to continue to evolve.
The real challenge here is that don't you have to make sure that the data that you trash is not valuable for what you're trying to do, and that you don't throw away something that's going to be essential for perhaps the safety of the car, right?
Well, absolutely. There's a number of key considerations when you start talking about new architecture, and we're just kind of looking at it a little more closely. One is the actual data traffic. And based on the amount of sensor data we talked about, the amount of data traffic on the network is increasing significantly. So you have to do real traffic analysis to plan for the type of network you want. We see Ethernet becoming very popular in terms of network adoption in the car. Usually it's Ethernet timing sensitive network because that allows you to put in policies and prioritization of the data. So data analysis, traffic analysis is critical to understand how big the bandwidth needs to be and to plan for the future. Because like we said, with OTA software updates, the applications, the amount of data can change based on how the software implements it. So you need to plan ahead, need to define the right traffic bandwidth and do that traffic analysis.
From a design perspective, really what you're doing is both partitioning as well as prioritizing, right?
Exactly. The heart of the new zonal architecture is a partitioning effort. So rather than having a central gateway that just multiplexes traffic, by having a zonal architecture, you can segment that pre-processing we talked about in the sensors and pre-processing in the zonal gateway locally. So that pre-processing doesn't affect the other application. But as we see, the heart of the zonal architecture is a central processing module. And in a central processing module, Using hypervisors and virtualization, you can have multiple applications running simultaneously in that centralized processing module. So along with the data analysis and traffic analysis, processing will increase as well.
To some extent, this sort of looks like a smartphone on wheels, right? I mean, that comparison's been made before.
And sure, Ed, we really think that the smartphoneization of the car is at the heart of this trend. It's multiple applications on that central processing module. It's a concept that a lot of the automakers are embracing, that vision of a centralized function, like a smartphoneization of the car. It is, I think, one of the trends that we're seeing.
By doing this, we also are now looking at this completely differently in terms of the movement of the data, right? So what impact does that have on things like wiring?
So that's a good point, Ed, because a lot of the benefits of this new zonal architecture does come across in terms of the wiring harness. So what I'd like to show is some of those savings and value of the zonal architecture, especially in terms of the data and the wiring harness. You probably all know the wiring harness is one of the most costly systems in the car to manufacture, primarily because it's all done manually. And so no robots in the wiring harness, as well as being one of the heavier systems in the car. So by using a zonal architecture approach, the wiring harness is using a central data pipeline. So the amount of wires are less, the weight is less, the system is much more simplified, so the cost is less, and also gives you the flexibility of a single maintenance point where all that processing occurs. So the maintenance is also less.
That gives you the opportunity to say, when something goes wrong, we can pinpoint it a lot faster, right, than we could if we had to go through and search every wire that's out there in every harness.
Sure. One of the benefits that the automakers are seeing, and this slide is being provided courtesy of one of the top tier ones in the industry, Visteon, is the fact that cost is less, power is less, maintenance is less. So there's a lot of benefits.
Given all of this, given all these different changes, what impact does that have on the SoCs that are used in vehicles?
Well, that's a great point to highlight is as the system architecture changes, the SoCs that implement those applications also change. And we're seeing the adoption of much higher performance interfaces and processing for those SoCs. So to build the electronic integrated circuits, just take a look at some of those changes. The interfaces, as we showed with the zonal architecture, is relying much more on Ethernet. And the current adoption of 10/101 gig Ethernet, we're seeing a dramatic shift to adopt higher speed Ethernet. I'm showing here up to 10 gigabit Ethernet. Using Ethernet timing sensitive networking, as I said, that allows you to put in policies for the data traffic and prioritize the data. You certainly want the safety critical data to have a higher priority based on maybe the infotainment type data. We're seeing the adoption of MIPI very broadly in the car because of all the image sensors. You may have seen a statement last year from the vice president of design at Waymo mentioning that there's 29 cameras in a Waymo self-driving car module. 29 cameras is generating a lot of sensor image data, and we see MIPI as being a very popular interface for image sensors. Because of those centralized smartphoneization processing modules, we see it's still going to be multiple chips, multiple SoCs. And PCI Express is the dominant point-to-point protocol to connect those multiple SoCs. And PCI Express 4.0 is widely used, but we're seeing a quick shift to the next generation PCI Express Gen 5, PCI Express 5.0. Because of the new applications in the car with the multiple software virtualization required, we're seeing a storage increasing for those centralized processing modules. So a shift from the different SSD protocols such as UFS to the more higher performance NVMe-based SSDs for storage. All these applications require external automotive-grade DRAM, and so we're seeing a very fast adoption of LPDDR5 DRAM and transition to the future LPDDR5X based automotive DRAM. So memory is always critical. And then, as we mentioned, just to process all the different applications, especially the sensor data such as imaging and LiDAR point cloud, we're seeing very prevalent use of AI in the processors. So deep learning, neural networks, convolutional CNN, and the different graphs and algorithms to implement that AI. So putting that all together, and not to forget security because of the high amount of connectivity in the car, the new networking implementation. Security is everywhere. Security concerns are everywhere. So to close any possible vulnerabilities, we're seeing a big adoption of different types of security, encryption, decryption, security HSMs, which are kind of root of trust implementation. So security is everywhere. That's a critical concern. So all these trends are affecting how we implement the integrated circuits, the SoCs, to implement those new architectures.
Because of this new architecture, is it easier to update than it was in the past? So you're more centralized. Does that help?
Well, like we said, the adoption of over-the-air software updates is certainly increasing. And there's a lot of system changes that need to be implemented to do OTA. The telematics, TCU, antennas need to be able to support the OTA. The networking, especially in the kind of packet processing, needs to support that OTA. And the software stack, the automotive grade OSs need to support that OTA. So across the board, updating the applications, either on the software side or future on the hardware side, needs to be planned in advance. And every one of the systems need to have that upfront support, upfront planning for those software updates.
Ron, given all of this, is it possible that this type of architecture will show up in other areas such as robotics and potentially medical devices, things like that, where you really do have to understand the same kinds of things that you're dealing with on the automotive applications?
Well, certainly in the large scale, like industrial systems that use robotics, absolutely. And then on the medical side, certainly the use of AI as these processing applications are more critical, that certainly will be adopted. So you have components of these new architectures and new processing modules being adopted beyond the automotive industry, absolutely. And then the fact that automotive is safety critical, a lot of these applications are safety critical. Those are the types of concerns that both the medical and industrial robotics adopters have as well, is making sure those systems are robust and can support those safety critical or applications.
Ron DiGiuseppe, thanks for a great explanation.
Sure, Ed, appreciate it. Nice to talk to you.